Here is a moment every person who has tried this knows. You type a prompt into an image model. You click Generate. Out comes something gorgeous, exactly what you pictured. So you click again, same prompt, same model, nothing changed, and out comes mush. Melted faces, wrong colors, a flat, lifeless mess. Same words, same machine, completely different result. And it is not random luck. Sitting between your prompt and your picture is a small panel of knobs that almost nobody explains. How many steps? Which sampler? How hard you push the guidance? Which random seed you started from? Turn one a little and a masterpiece becomes garbage, or garbage becomes a masterpiece. This episode is about that panel. By the end, you will know what each knob actually does, why the defaults sometimes betray you, and how to run the whole thing yourself on your own computer for free. Not magic words. The machine underneath the magic words. To read the knobs, you first have to be honest about what the model is doing, because the popular picture is wrong. It is not searching a giant library and pasting bits together. It is not collaging stolen images. It is not opening a hidden photo and cleaning it up in Photoshop. Here is what actually happens. The model starts from pure random static, a screen of noise with no picture in it at all. Then it takes a guided walk. Step by step, it nudges that static a little less random, a little more like the kinds of images it learned from, until a coherent picture settles out of the fog. Think of it geometrically. Every plausible image is a point in a vast space, and during training the model learned the thin surface where the real, sensible images live. We will call that surface the manifold. Generation drops a single dot of noise somewhere off that surface and walks it downhill until it lands on the manifold, on a fresh point that nobody placed there by hand. That is the whole picture. Now every knob on that panel is just a different way of controlling that one walk, where the dot starts, what steps it takes, and how hard it gets pulled toward your words. One quick callback before the knobs, because the internet muddles it constantly. In the painting episodes, we settled two things, and you only need them in one line each here. First, diffusion and flow matching are not rival camps. Flow matching is the general recipe for that downhill walk, and classic diffusion is just its Gaussian special case. Same family, not a feud. Second, the arrow the model follows at each step goes by three names: removing noise, the score, the velocity, and they are one arrow in three costumes, not three different machines. With that parked, here is the only part that changes how your knobs behave. The newest models learn to make that walk nearly a straight line instead of a long meander, and a straight path needs far fewer steps. That single fact is why a picture that once took 50 steps can now take 4. And it is the reason the steps knob behaves so differently from one model to the next. Now the first real knob, the seed, and it is the most misunderstood one. The seed is just a number, and that number decides exactly which patch of random static you start from. Same seed, same starting noise every time. Change the seed by 1 and you drop a completely different noise dot somewhere else off the manifold, which walks down to a completely different picture. So the seed is not a quality setting. It is which lottery ticket you are holding. And here is the surprising part. That starting noise is not neutral. The walk is so sensitive that some starting points lead to crisp, faithful images and some lead, with the very same prompt in the very same settings, to a mangled one. People burn hours rewriting their prompt when all that changed between a great result and a bad one was the seed. Two practical payoffs. 1. When you finally get an image you love, lock the seed, and now you can change one small thing in the prompt and keep almost everything else. 2. If a result is close but slightly off, do not panic and rewrite everything. Roll a few new seeds first. You are not editing the picture. You are choosing a different place to start the walk. Next, two knobs that work together and confuse people the most: steps and the sampler. The sampler is the thing that actually takes the walk. The math underneath is a smooth, continuous curve from noise to image, and the sampler is the method that chops that curve into a finite number of hops you can compute. Steps is just how many hops. And here is the rule nobody tells you. There are two kinds of samplers, and they behave in completely opposite ways. The first kind is deterministic. Names you will see are DDIM, Euler, DPM++, UniPC. These walk steadily toward the answer and then settle. For a typical model, somewhere around 20 to 30 steps, the picture has basically converged. After that, more steps cost you time and change almost nothing. The second kind is ancestral, often marked with a small a like Euler A, and the SDE samplers. These sprinkle a little fresh randomness back in at every single hop. The effect is strange and important. They never settle. Add more steps and the image keeps changing, not getting better, just different, wandering forever. So the famous advice, more steps equals better, is a half-truth. Past the point where a deterministic sampler has converged, extra steps are wasted, and for an ancestral sampler, more steps never converges at all. The honest move is to pick a good sampler, find the step count where it stops improving for your model, and stop there. Now the knob that does the most damage when you crank it, guidance, usually labeled CFG, classifier-free guidance. Here is the mechanism, and it is clever. At each step, the model actually makes two predictions. One with your prompt, one with no prompt at all, a blind guess. Then it looks at the difference between them, the part of the move that your words are responsible for, and it exaggerates that part. The guidance scale is how much it exaggerates. Picture it as a force vector pulling the walking dot. Turn guidance low and the pull toward your words is gentle. The dot wanders freely. You get variety, but it may drift from what you asked for. Turn it up and the pull gets stronger. The picture hugs your prompt more tightly. So far it sounds like more is just better, and this is exactly the trap. Push the guidance too high and that force yanks the dot clean off the manifold, off the surface where real images live, out into a region of impossible pictures. The result is what people call fried. Blown out colors, hard edges, a burnt oversaturated look, and oddly less variety, because everything collapses toward the same overcooked answer. Guidance is not an accuracy knob. It is a tension knob, prompt faithfulness on one side, natural and diverse on the other, and the sweet spot for most models is a moderate middle, not the maximum. There is a twist on guidance that trips up almost everyone in 2026, and it is worth 2 minutes because it explains a very common silent failure. Running the model twice at every step, once with your prompt and once without, is slow. So newer models were trained to skip the second pass. The guidance behavior gets baked directly into the network during training, which is called guidance distillation. On its own, that just makes each step run once instead of twice, about twice as fast. A separate trick, step distillation, is what teaches the fast models to finish in just 1 to 4 steps instead of 50. Many of the newest models use both. Great for speed. But baking guidance in has a consequence people rarely realize. The classic negative prompt, where you list things you do not want and the model steers away from them, worked by hijacking that second, prompt-free pass. In a guidance-distilled model, that second pass is gone. So on many of these fast models, the negative prompt box does nothing. People paste a long list of things to avoid, feel reassured, and it is quietly ignored. 2 takeaways. First, know which kind of model you are running because the same setting that is powerful on one is dead weight on another. Second, a quick callback to the GANs and VAEs episode where we made this exact point. These fast distilled models are built using an idea from GANs, and the compressor that turns your latent back into pixels is a VAE. Just as we said back then, neither is dead. They went from headline acts to essential parts working quietly inside the machine you use every day. Before we leave the knobs, one promise the internet makes that you should not fully trust. Same seed equals same image everywhere forever. It is true, but only inside one fixed setup. On one machine, one software version, one numeric precision, the same seed and settings will reproduce the same picture down to the pixel. That is genuinely useful and worth relying on. But move that same seed to a different graphics card, a different attention implementation, or a compressed version of the model, and it drifts. The picture will look like a close cousin, recognizably the same idea, but not pixel for pixel identical. The reason is humble. The tiny arithmetic operations that run on a graphics card are not guaranteed to add up in the exact same order on different hardware, and those microscopic differences compound across hundreds of steps. So when you see two people online getting different results from the same seed and the same prompt, do not assume one of them is lying. They were almost certainly running different hardware or a different build underneath. Reproducibility is real, but it is local to your exact setup, not a universal law. Now the second half of running it yourself, actually running it yourself on your own computer for free. The whole open ecosystem lives in two tools. The first is a library called diffusers, the standard way to drive these models from a few lines of code. The second is Comfy UI, the popular visual runner, where every part of the process, the noise, the sampler, the guidance, the decode, becomes a box on a canvas that you wire together with cables. Every knob we just discussed is a literal slider or input on that canvas. Seeing the pipeline laid out as connected boxes is, honestly, one of the better ways to understand it, because the abstract walk we have been drawing turns into a thing you can poke. One honest aside, since this channel cares about it. Learning to run this tool is not the same as using it to make a channel's teaching visuals. We are teaching you the machine. What you create with it is your call, and the line that matters is consent, which we will come back to. The real wall between you and running any of this is not the software. It is free. The wall is memory, the kind of memory on your graphics card, and that is the last piece to understand. So why can your friend run this and you cannot on similar-looking computers? One word: VRAM, the dedicated memory on your graphics card, where the model has to physically sit while it runs. A strong open image model in 2026 can be a heavy thing. At full precision, one popular open model needs somewhere around 30 gigabytes of graphics memory just to load, which is more than almost any home computer has. Game over before you generate a single picture. This is where one beautiful trick rescues the free local creator, quantization. The model is billions of numbers, and normally each number is stored at full precision, taking a lot of room. Quantization rounds those numbers to a coarser, lighter format. The same model, same abilities, packed smaller. Watch what it buys you. At full precision, around 30 gigabytes off the table for most people. Compress it to an 8-bit format, and it drops to roughly 13. Compress it further to a popular 4-bit format, and it fits in about 7, which means it now runs on a modest 8-gigabyte card, the kind in a mainstream gaming laptop. The model just went from impossible to runnable on hardware you might already own. There is, of course, a catch, and you should hear it honestly. The gentle compression is nearly free. At 8-bit or 5-bit, almost nobody can tell the difference in a blind look. But push too far down to 4-bit and below, and fine detail starts to soften. Textures get a little mushy, small text gets shaky. So quantization is not magic with no cost. It is a brilliant, mostly free trade, right up until it is not. The exact numbers will keep shifting as models and cards change, but the shape of the trade is permanent. Smaller format, less memory, slightly less detail. Which leaves the honest final question. Should you run it locally at all, or just use a website that does it for you? This is a real trade-off, not a free lunch, and it is worth being clear-eyed. Run it locally and you get 3 things. It is free per image, no matter how many you make, so you can generate 10,000 experiments and the bill is the same as 0. Your prompts and pictures never leave your machine, which matters if you are working on anything private. And you have total control, every knob custom models, no content filter deciding for you. The cost is that you are capped by your own hardware. A top cloud card will be faster, and the quantization you needed to fit your card costs you a sliver of quality. Use a hosted service instead and you flip every term. You get the very best quality and speed with no setup, but you pay per image. You wait in line behind rate limits. A filter sits between you and the output, and your data leaves your control. And a fair warning on the polished hosted models with famous names. How they work inside, their exact settings, their training is mostly undisclosed. You can admire the results, but you cannot study the machine, which is the quiet case for learning the open stack. It is the one place where every knob is yours to see, to turn, and to understand. So here is the whole episode in one breath. The same prompt gives a masterpiece or mush because of where the walk starts, how it steps, and how hard it is pulled, and the only thing standing between you and running that walk yourself is a little memory and a willingness to turn the knobs on purpose.